Welcome to Part 3 of Module 8. The learning outcomes for Part 3 of Module 8 are solve questions relating to titration and write total and net ionic equations. Titration is the reaction of an acid and a base to form salt and water. A titration measures the volume of one reagent required to react with a measured mass or volume of another reagent. A titration is used to determine the unknown concentration of an acid or base in a sample. An indicator is used to signal the endpoint when stoichiometric amounts of acid and base are present, or in other words, the indicator will give an idea of when we have equal concentrations of acid and base. A burette is used to deliver the titrant into an Erlenmeyer flask. For example, if 22.59 milliliters of 0.1096 molar HCl is used to titrate 25 milliliters of sodium hydroxide to a phenolphthalein endpoint, what is the molarity of sodium hydroxide? This example is very similar to the stoichiometry questions we covered in Module 6. The first thing to do is to check if the equation is balanced. Then we can use the table we learnt in Module 6. We have the acid molarity, 0.1096, but we can't work with that, so we need to calculate the number of moles. Remember that molarity equals moles over volume, so by rearranging the equation, we find that moles is equal to molarity times volume in liters. From the question, we have 22.59 milliliters of HCl. So the number of moles is 0.002476. The ratio between HCl and sodium hydroxide is 1:1. So the number of moles of sodium hydroxide is also 0.002476. We need to calculate molarity, and we have moles and volume. So 0.002476 over 0.025 liters gives us 0.09903 molar. If you check your textbook, you will find a different approach to solve the question. We will learn this approach too, and you can choose the one you find easiest to use. So, from the question, we know the following. We need to calculate the molarity of the base. First, we calculate the moles of the base. To do that, we need to undertake the following calculation. Volume of the acid, 22.59 milliliters, times molarity of the acid, 0.1096 moles over 1,000 milliliters, times the ratio between the acid and the base. So 1 mole of base, what we want, over 1 mole of acid, what we have. We then cancel the similar units. The answer is 0.002476 moles of sodium hydroxide. The molarity will be 0.002476 moles over 0.025 liters to give our answer of 0.09903 molar. Remember, you only need to do one method to solve the question, and it is up to you to choose which one. Let's try another example. What is the molarity of sodium hydroxide solution if 21.93 milliliters of NaOH is required to titrate 0.243 grams of oxalic acid, which is H2C2O4? In this example, we start from the mass of the acid, 0.243 grams. We go from mass to moles using the molar mass from the periodic table, which is 90.04 grams per mole. Thus, the number of moles is 0.002699. The ratio is 1:2, so the number of moles of base is twice as much as the acid, giving 0.005398 moles of base. We need to calculate molarity, so we divide by the volume in litres. The molarity is 0.246 moles per litre. Now we'll try the textbook method. We know the following information from the question, and we need to calculate the base molarity. So we calculate the moles first using the following calculations. Mass of acid, 0.243 grams, divided by the molar mass, times the ratio. Cancel the similar units, and the answer is 0.005398 moles of sodium hydroxide. The molarity of the base is the number of moles divided by the volume in litres, so 0.005398 over 0.02193 will give us the answer of 0.246 molar. What is the concentration of a nitric acid solution if 10 milliliters of the solution is neutralized by 3.6 milliliters of a 0.2 molar sodium hydroxide solution? Please stop the video and try to solve this question. The answer will be revealed after you proceed. The answer should be A, 0.072 molar. Neutralization is the reaction between acid and base to produce salt and water. For example, HCl plus NaOH gives H2O plus NaCl. This reaction can be written in ionic form to show the ions coming from the electrolytes. This is what we call the total ionic equation. H plus Cl minus plus Na plus OH minus gives H2O plus Na plus Cl minus. HCl and NaOH are both strong acids and bases respectively, so they completely dissociate. In the product we find water, which is a non-electrolyte, so it doesn't dissociate. Sodium chloride is soluble, so it gets ionized. This is our total ionic equation. Now we can remove the spectator ions, or the ions that are not participating in the reaction. So these ions are found on both sides of the reaction. For instance, we can see the chloride ion on the left side and the chloride ion on the right side, so we can cancel them. Likewise, the sodium ion is found on both sides. After removing these ions, we get the net ionic equation. In this example, H plus OH gives H2O. The net ionic equation tells us that the driving force for the reaction is the reaction between the hydrogen cation and the hydroxide anion to form water. There are a set of rules to write the ionic equations. First, strong electrolytes, that is, the strong acids and strong bases, in solution are written in their ionic form. For example, sodium hydroxide is written as Na plus OH minus. Weak electrolytes and non-electrolytes are written in their molecular form. For example, H2O and acetic acid. Solids and gases are written in their molecular form. For example, CO2 and AgCl. The net ionic equation does not include spectator ions. For example, Na plus OH minus plus H plus Cl minus gives Na plus Cl minus plus H2O is the total ionic equation. When we cancel out the spectator ions, we get OH minus plus H plus giving H2O. And this is the net ionic equation. Equations must be balanced both in atoms and in electrical charge. Let's practice an example. The reaction between barium chloride and sodium sulfate will produce barium sulfate and sodium chloride. The reaction is balanced. To write the ionic equation, we need to figure out which compounds are electrolytes and which are not. In the reactant side, both barium chloride and sodium sulfate have an aqueous symbol next to them, so they are soluble. On the product side, we know that sodium chloride is soluble. However, if we remember from Module 7, barium sulfate is not soluble. You can confirm that by the S symbol, which means it is a solid compound. Now let's write the total ionic equation. Ba2 plus 2Cl minus plus 2Na plus SO4 2 minus gives BaSO4 plus 2Na plus 2Cl minus. To write the net ionic equation, we need to remove the spectator ions. So the net ionic equation is Ba2 plus SO4 2 minus gives BaSO4. We will look at another example. Write the chemical reaction between sodium bicarbonate and hydrochloric acid. Remember that carbonate in the reactant means we get carbon dioxide gas as the product, or as one of the products. Also check that the reaction is balanced. So the total ionic equation looks like this. 2Na plus CO3 2 minus plus 2H plus 2Cl minus gives 2Na plus 2Cl minus plus CO2 plus H2O. Let's remove the spectator ions and write our net ionic equation. CO3 2 minus plus 2H plus gives CO2 plus H2O. What is the net ionic equation when hydrobromic acid reacts with potassium hydroxide? The answer should be A. This is the end of Part 3 of Module 8. In the next two slides, we will review the key concepts that we covered in Part 1 and 2 of this module. In Part 1 of Module 8, we introduced the different definitions for acids and bases. Arrhenius defines acids as substances that increase proton concentration in the solution. Bases are substances that increase the hydroxide ion concentration. Bronsted-Lowry theory defines acids as proton donors and bases as proton acceptors. We also introduced the concept of conjugate acids and conjugate bases. The conjugate acid has one extra proton than the base. We can also say it is more positive than the base. The conjugate base has one less proton than the acid, so we can also say it is less positive than the acid. A neutralization reaction happens between an acid and a base to produce salt and water. Acids react with metal carbonates to produce salt, water, and carbon dioxide gas. Acids react with metal oxides to produce salt and water. And finally, acids and metals react to produce salt and hydrogen gas. In the second part of this module, we introduce the concept of electrolytes as chemical substances that ionize in water to produce cations and anions. They are also able to conduct electricity. We define strong acids and strong bases as strong electrolytes that dissociate completely in their solutions. Some examples of strong acids include hydrochloric acid and sulfuric acid. Some examples of strong bases include sodium hydroxide and calcium hydroxide. Weak acids and bases are weak electrolytes. They don't ionize well, and most of the solution will contain the molecular form of the compound. The only weak base that you need to learn for this course is ammonia. After that, we discuss the concept of pH as a logarithmic scale. When the pH is 7, then the solution is neutral, and there are equal concentrations of H+ and OH- ions. pH has a range from 0 to 14. However, the values can exceed this range in some solutions. This is the end of Module 8. Please practice the weekly exercises in your textbook and the questions you find in your workbook. We will meet face-to-face in the tutorial sessions, and this will be your opportunity to ask any questions or seek further clarification.